Okay, so now we are ready to solve the exercises. In fact, we are so ready that we already have solved these first four. So let's see what they are. In the first one, we have been asked to do this, that is, in the proof of lemma 531, if you go back to the actual statement, I am not going to repeat those things again. Prove that the degree of the polynomial qx is 1 less than the degree of px, which we have already done. When we proved lemma 531, there itself we did it. Then in so that means this one is already there, it is solved. Then in exercise 2, we have this. In the proof of theorem 531, prove in all detail that these elements form a basis of E over F. Now here, if you recall, we were given a polynomial over some field F and we were trying to find an extension E of F which will have at least one root of that polynomial. And in fact, I think here the polynomial was irreducible also. I can't remember exactly, but whatever the case, say that polynomial is px. What we then did, we considered the principal ideal generated by this polynomial in the polynomial ring fx, and we considered the quotient of the polynomial ring fx by this ideal, and in fact this is the thing that we called E. And then we of course saw that E has a root of this px, and E needs to be an extension of f, that means E needs to be a field. So yes, I think the px that we were given in the statement of this theorem was irreducible, because when px is irreducible, the principal ideal it will generate will be a maximal ideal, and hence this quotient will be a field. But while proving this thing, we in fact did this whole thing. We showed from scratch, that is in all detail, that these elements in fact form a basis of this vector space E over F. Okay, so this one is also there for us. We have already done this. So we have this one also. Then in exercise 3, prove lemma 533 in all detail, which in fact was just this statement that if you have two fields f and f prime that are isomorphic to each other by some isomorphism tau, then there exists an isomorphism tau star that maps fx onto f prime t, and the corresponding polynomial rings are also isomorphic, and some other conditions are also there. That is, if you apply tau star on the elements of f in particular, then something happens. Okay, so this also we have already done. So that means this is also available to us. And finally, the next stage is this one, which also we have done. So here we take the next step and consider the map tau double star in lemma 534. We have to show in this exercise that it's a well-defined function and is an isomorphism of this quotient ring onto this quotient ring. This is also something we have already done. So let us now see the next one, that is exercise 5. In exercise 5, we recall one of the 3 examples that we saw at the end of this section, and that means actually example 3. So in example 3, so this is the 5th one. In example 3, at the end of this section, prove that the extension f omega is the splitting field here is the splitting field of this polynomial. In that example, we of course were discussing about the splitting field of this polynomial, where we already know that f denotes the field of rational numbers, and we came across this number omega in example I think 1 itself, 1 or 2. So we now have to prove that if we attach this omega to the field of rational numbers and get this extension, then this itself is actually the splitting field of this polynomial. So let us now show that. We know that omega is actually this complex number, which is not a real number. And which is a well-known complex number. In fact, it is one of the 3 cube roots of the real number 1. It is a cube root of unity. Now one can verify these 2 properties of this number. Which is something that most of us have already seen, that if you take the expression of 1 plus omega squared, then you get 0. And when you take the cube of omega, you get 1. And in fact, that's why it's a cube root of unity. But still, we will just quickly verify these things also. So let's just first write, one can verify these 2 things, and omega cube equals 1. Now using these relations, using these equations, it can be shown that our given polynomial has this factorization. X minus omega squared times x plus omega squared. Okay, it can be shown that this is how the polynomial can be completely factorized. Now note one thing, what is it that we are going to do here? Our aim is to show that this extension of f, which of course is a field, it's a subfield of the field of complex numbers. is the splitting field of this polynomial. So what are the criteria? The criteria are these. First of all, this field should contain all the roots of the polynomial. There would be 4 roots because the degree is 4, and from this factorization we can actually see that those 4 roots are omega, minus omega, omega squared and minus omega squared. So are these things here? Yes, they are, because by definition omega is in this field, in this extension, and that is why, because it's after all a field, minus omega is also there, and that's why plus or minus omega squared are also here in this extension. So it satisfies the first criterion, that it contains all the roots of the given polynomial. But then it also has to, but that is not enough for it to be the splitting field. It also must have the smallest possible degree. Having all the roots and simultaneously it must be of the smallest possible degree as an extension over F. Okay, so let us just first mention that it has all the roots. Hence, contains the 4 roots of the polynomial Okay, so next comes the question of its degree over F, and the degree of course would be equal to, because now we know the theory. What is the degree of this over F? It is equal to the degree of the minimal polynomial of omega over F. Okay. So, but then the question now becomes, what is the minimal polynomial of omega over F? F is the field of rational numbers. This just means that we should find now a polynomial with rational coefficients, and that too not just any polynomial, a monic polynomial with rational coefficients which is satisfied by omega. That is the first thing, and such that it has the minimum degree among all such polynomials. But you see, we already have one such thing here. So next we write things omega satisfies the polynomial. We could have just written, instead of writing omega satisfies the polynomial 1 plus x square, we could have just simply written this equation, but we want to emphasize the fact that the polynomial omega is satisfying is actually a polynomial over the field of rational numbers. The polynomial x squared plus x plus 1 in this polynomial ring where f is the field of rational numbers. So what does that mean? That immediately tells us at least something about the degree of f omega over f. Hence, the degree of f omega over f is less than or equal to 2. So that means now there are only 2 possibilities. Either the degree will be 2 or it will be 1. Note that if we suppose that this degree is actually equal to 1, then of course we must have this f omega should be equal to f, because that is the only case in which degree becomes 1. And so omega must belong to f, because omega belongs to the left hand side by the definition of this extension, so it must also now belong to f. However, this is not possible. Why? Because f is the field of rational numbers, so that means f is, after all, the things in f are real numbers. However, this is not a real number. But this is not possible. So that means this supposition cannot be made. So now we are down to only one possibility, that is the degree has to be equal to 2. So the degree has to be equal to 2. This shows that f omega is an extension of f containing all the roots of the polynomial and of minimum degree, and that is why it's the splitting field of the polynomial. And that's where the solution stops. Now, actually, where is this minimality coming from? See, the minimality is coming from the fact that f omega has been found to contain all the roots of the given polynomial. Okay. But at the same time, no other, and already we are having the degree of f omega over f to be equal to 2. So we have in fact already got an extension whose degree over f is quite small already, it's just 2. So is there any room for even smaller degree? No, because if you assume that there is in fact still some field, some extension of f which has all the roots of this polynomial, and at the same time its degree over f is 1. Okay, but then that extension must be equal to f. which however which would then make you conclude that you have a contradiction like this, because that extension, say you assume that E is an extension of f which has all the roots of this polynomial, but its degree over f is 1. But then, as we have seen what happened with this one, E will be equal to f, but then again you face the problem that omega would not be in E because it's not in f. So how is E containing all the roots of the polynomial? So that is why such a degree 1 extension cannot in fact contain all the roots of the polynomial. In fact, that degree 1 extension is nothing but f itself, which does not have omega. So it's not a splitting field. It does not split the polynomial fully. In fact, it does not split the polynomial at all. And that's why we can now safely conclude that f omega itself is the splitting field that we are seeking. And because of the results that we proved in this section, that a given polynomial has essentially a unique splitting field. So this is just the thing. If you encounter another splitting field in some other fashion by some other means, then you know from theory that that splitting field is essentially just this one. It's that they are isomorphic to each other. And now, before I finish, because I am not going to do anything else today, let us just also see some of the things that we just casually mentioned in the actual solution. The first thing is this. You may already know this, you may not know this, you may have also forgotten. So let's just see if it's actually true or not. It is, but let's just see. If we take the square of omega, what do we get? So we would take the square of the numerator, a square, minus we would get 2 root 3 I plus root 3I whole square, that means minus 3, divided by the square of the denominator, that is 4. So that means we are getting minus 2 root 3I divided by 4. And now there is a cancellation, of course. So we are getting here minus 1 minus root 3 I divided by 2. So now if you take the sum of omega and omega square, there itself we have a cancellation. Root 3I divided by 2 minus root 3I by 2, so they cancel out. And we are left with minus 1 over 2, and here also minus 1 over 2. That means omega plus omega square is minus 1 over 2 minus 1 over 2. That means minus 1. Or you are getting this. And what about the next equation, that omega cube being 1? Let's just see that also. Omega cube is omega times omega square, and that thing equals divided by 2 2's would give us 4. Now if you perform the multiplication, what do you get? minus 1 minus 1. Of course I can use the formula, but I just want to do it directly. 1, so we are multiplying by minus 1, so we get this, and then I multiply by this. Minus root 3, they give me 3, but we have I square, so it becomes plus divided by 4. So you can see that you are getting 4 divided by 4, so that is 1. So yes, omega cube in fact is 1. And there is also one more thing we mentioned, namely that factorization. So let's just see that if we multiply these polynomials out, do we really get that polynomial? I mean our given polynomial. So if you multiply the first two, you are of course going to get x squared minus omega squared, because x minus omega times x plus omega. Similarly, here multiplying these two out, you get x squared minus omega to the power 4. Okay, but here of course in place of omega to the power 4 you can write just simply omega, because the cube of omega is 1. And now we perform the final multiplication. X to the power 4 minus omega x squared minus omega squared x squared minus minus will become plus omega cube. So omega cube is 1 of course. Now if we take the x squared terms together, we get this times x squared plus 1. Now from this equation, that this is equal to minus 1, so the minus of this would be plus 1, that is this. And that's how we see that yes, we are actually getting the given polynomial. So that is why this is this is the factorization, I should say, of this polynomial over the field of complex numbers in general. So the coming few problems that we are next going to see in the next video, they will be like this. We won't of course be asked to find the splitting field itself, but we will be asked to figure out the degree of the splitting field over the field of rational numbers. And there it's always the best if we really are able to factorize the polynomial fully, so that we will know all its roots, and then of course we can figure out the smallest field having all those roots. But even when you are not able to find the splitting field explicitly, there also you will be able to say something about the degree, and in fact in some such cases you will be able to actually determine the degree, although you may not be able to give the splitting field itself, but you will know what its degree is over the field of rational numbers. So with that I end this video. It's not necessary that we should always make extremely long videos. Sometimes short videos are also okay. So that's just it. I wrap things up for tonight. If you want to say something, you can of course use the comment section below, or you can mail me. My mail address will be there in the description. And this coming Friday, let us again do vector spaces. So that's just it. So see you on Friday with vector spaces. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.